Well, last time we spent a long time working problems on proportions, which is mostly a review, but it's been such a long time since you've seen it. I'm sure it didn't hurt to go over it again. Remember, we had one property of proportions. It started with, if we had something like this, a over b equals c over d, then we could write remember, this was our first property of ratios. If we have a over b equals c over d, then AD equals BC. Now, from this property, I think we can directly show that this statement is true. How do we do that? Well, I would multiply by 1 over a first. Multiply by 1 over a here and 1 over a here. Well, 1 over a times a is just going to be 1, so we get d on this side. And b over a times c on this side. Now, and we should actually write it out explicitly just in case. 1 over a and 1 over a. Now here, we multiply through by 1 over c. And you get that d over c equals b over a, and that's this right here. Oops, that wasn't very good. That's that right there. So this is definitely true, and it's pretty easy to see why. What about the next one? What about the second property here? We can interchange the means. In other words, we can switch C and B. Well, we can demonstrate the truth of that fairly easily also by starting with our original property of ratios. Given this, then AD equals BC. Now, all we have to do, very similar to what we did before, multiply through by 1 over c on each side and get AD over c equals b. And now, I'm sure you've guessed what we're going to do. Multiply through by 1 over d on each side. And what do we get? Of course, a over c equals b over d, which is the statement right here. So these are both fairly easy to derive from the very first property we had, which was our cross product. The product of the extremes equals the product of the means. And now this last property here, which says, how do they write it? If you add the denominator to its numerator, you get a new proportion, and it turns out that they're still equal. In other words, like it said, you just stick a b up here and a c up here, that gives you a whole new proportion, and magically these still turn out to be equal. Well, actually, it's not magic at all. It's pretty simple. Think of it this way. A over b equals c over d. Well, that means that our addition property of equality says we can add the same thing to both sides. So let's add 1 to both sides. Well, what's another way of writing 1? Well, in this case, how about we write b over b? That way we have a common denominator. And this will be a over b. And over here we have c over d plus 1. Well, what's another useful way of writing 1? How about d over d? So what do we end up with? We have a common denominator here, so we can write a plus b over b. And here we write c plus d over d. Well, that pretty much looks like this, doesn't it? That's all you had to do was spot that this b over b is the same as adding 1 to each side. And then you've got this. Now these are all fairly simple. I don't think you'll have any trouble at all with this section. So let's start working some geometry problems using these proportion things. What do we got here? They're telling us that the ratio of xw, that's this line here, to xv, that's the big one here, is the same as the ratio of yw, that's this, to cv. Well, it's a lot of stuff going on here. See if we can make sense out of this. Now, our job, as they say, is to find zv. So let's start putting numbers in here and see if this problem actually makes any sense. How about xw? What's that? Well, that's 12. What's xv? Well, that's these two segments here together. So that's 17. And that equals yw. It's right here, that's 24. Over, and that we don't know, that's x. So, let's use obviously it's legal to use any of your properties of proportions or the things you already know about algebra. In this case, let's use what they've been telling us. Algebraically, you can solve this pretty quickly too, I think, if those of you who remember your first year of algebra well. But we'll do it with the multiplying the means and the extremes, which will also give us a fairly simple equation that 24 times 17. Here we get the means here, and the extremes here. 12x is 24 times 17. Suppose we multiply through by 1 over 12. This will just become x, and this will be 2 times 17, or 34. So this longer side down here, this is 34, and what we've discovered is that 12 to 17 is the same as 24 to 34. Same ratios. Well, there's another one of those someone made a mistake problems. What did they do wrong? Well, it looks like they tried to apply the property that says we can add the denominator to the numerator on each side and still end up with a true proportion. Well, they added the denominator to the numerator here, but then they added this denominator to this numerator over here. You can't do it that way. You have to keep it straight. This this denominator goes with this numerator, and this denominator goes with this numerator. You can't mix it up the way this person did, so this really should have been c plus 4 over 4. If you'd written a plus 3 over 3 as c plus 4 over 4, boom, that would be correct. Here's another problem. It's very similar to the first one we did. Might seem a little strange that we're working such simple problems. All we're really doing is using fractions to solve simple little algebraic problems. You did that last year. Well, these problems are also demonstrating subtly some facts about these geometric objects, in this case triangles. For instance, they're saying that CA, that's this whole large length here, over CB, that's this small one, is the same as this long length here, AE, over BD. But what is BD? Well, that's the line that runs parallel to this and cuts this side according to these two proportions, CA and CV. So what they're really getting at here, and we're going to prove it in another section or two, I forget exactly when it comes up. It's no accident that these proportions are the same, and they're not just making this up. These proportions really are the same. When you break this line up into two proportions, you end up creating two more lines if you break it up with the line parallel to this one, which also have the same proportions. We'll do much more of that in the next couple of sections, but pay attention to what we're doing here and how these ratios are working out, because it's going to come up in the next couple of sections where I can actually prove why these ratios hold, or prove that they do anyway. So what is CA over CB? Well, CA is the 14 plus the 7. It's the whole thing. And CB, well, that's 14. And that equals AE is 18 over BD. That's this one here. We don't know what that is. Just going to call it X because it's easier. I could have written BD. We could have, down here instead of X, I could have written, maintain the symbol, but it's easier just to write X. And X, when we carry it all through, if we end up with more complicated equations, which sometimes in this class you've seen some pretty long equations that took half the page, writing BD with a line over it, it just seems like a lot of unnecessary writing. X was tailor-made to be the unknown variable. It was born to be unknown. So just go ahead and use it. And again, we're going to use our product of the means is equal to the product of the extremes. So we get 21x equals 18 times 14. There. We can simplify these, like divide through by 7, and we get 3x equals 18 times 2. And then multiply through by 1/3. And we get 18 over 3 is 6 times 2. So x equals 12. What about this over here? DE. Well, they just threw that in to help you get confused. It had nothing to do with the problem. And again, you can see that solving these for x is actually very easy. The reason they're showing you this is for you to get used to the idea that there's a whole lot of proportions. When you start breaking up triangles, it turns out that the proportions that exist in one spot exist somewhere else too. And you created them yourself by dividing a side somewhere. It'll make a lot more sense in a couple of sections when we actually lay it out more rigorously. And there's a multiple choice that just tests your knowledge of the properties of proportions. For instance, what it wants to know is which of the following is false. Which of these won't be true if this proportion holds. Well, let's see here. y over x equals q over z. Well, y over x, q over z, this is the reciprocals. This is the reciprocal of this is the reciprocal of this, and we know from our properties of proportions that the reciprocals are also equal. So this one's true. How about this? xz, x over z is equal to y over q. Well, here we exchange the extremes. Is that okay? I said that wrong. We didn't switch the extremes. We swapped the denominators on this one. We went from... Did we? No, that's wrong too. I'm not sure what we did on this one. Doesn't look like it would be true. Let's check the others first, and then we'll figure out what we did to arrive at this one and see if it actually made sense. How about this? Y over x. Well, this is the reciprocal. Z over q. This one isn't. So we have the reciprocal equal to the original. That doesn't make any sense. So this is probably the one that's false. And what about this? Well, we already know this is the third property we looked at just a little bit ago, where we can add the denominator to the numerator. So this is legit. This one here, which property does this demonstrate? Let's see here. Looks like we interchanged the means, didn't we? We moved y over here and z down here, and everything else is the same. And we have our second property that we saw today, property of proportions, which says we can interchange the means. So this one is okay. This one's okay because we just inverted both of them. This one's okay because we interchange the means. This one's okay because we added the denominator to the numerator on each side. So, but this, here we have an inverse, and here we have the original, and that's no good. So, this will be our false choice. And here's one, which is good because it's good to understand map scales. And unless you enjoy getting lost, I guess, then the heck with it, who cares about them? But most people prefer not to be lost. The joys of dehydration, starvation, and fatigue are lost on most people. So we've got a street that's 3 inches long on the map, but it's actually 1 mile long. Now sometimes scales are written as an improper ratio. In other words, you could right off the bat write 1 inch equals 1/3 mile and say that's the map scale. And on some maps it would actually be written that way in the legend. But that's not what they mean here. They're looking for something like 1 to something else. Like 1 to 10,000 or something like that. Meaning 1 inch on the map would be 10,000 inches. Well, this requires conversion. So that's pretty easy to do, really. We have 1 mile is, let's see here, 5,000. In order to convert the mile to inches, and naturally that's going to be a big number, we'll use something, the easiest way I think is to just keep all your units straight in the form of a fraction and then multiply through. In other words, 5,280 feet per mile. If we multiply that through by 1 mile, then we'll get 5,280 feet. 12 inches per foot. The foot cancels, and we multiply the 12 times the 5280, and we will get the number of inches in a mile. So if we do that, we get 63,360 inches in a mile. So we can start off by writing our scale as 3 to 63, 360. But that's not the way you usually write a scale. It's better to reduce it. For instance, if we can get a 1 here, where the 3 is, that'd be better. And if we divide this, in other words, we could write this, to reduce it, it's usually easier to think of it as a fraction. That's one way to do it. Or just divide through. For instance, divide this by 3, and divide the one on this side of the colon by 3. That also reduces it, in which case we get 1 to 21 something. 21, 120. So this is the scale without units. This is inches to inches, so we can just drop the units, and that's the scale, because that scale is true. This scale right here is true no matter what units we have. 1 mile on the map, if you could make a map that big, would be 21,000 miles. Would represent 21,000 miles. 1 foot on the map would represent 21,000 feet, 21,120 feet. 1 meter on the map would represent 21,120 meters in the real world, I guess you could say. Well, this one's really pretty easy. Just have to think back to what we remember about slopes. Pardon me, I left out one fairly important part of this problem. You need to know the slope of the wheelchair ramp. Without that, you can't work this problem. Now they have the slope is set at 1 over 12. That's around 8% grade, and as they point out, that's about the maximum. Some of these slopes are actually steeper than they sound. Doesn't sound like much, but if you get up to like a 20% grade, that's actually kind of steep. Well, anyway, this is a good use of proportions. Remember, the slope is the rise over the run. And in this case, we know that the run, that's the length of it. You know, if we had a wheelchair ramp, it kind of goes like that, except that this is actually straight, and it definitely wouldn't be that steep. Well, this is from here to here. Remember, that's the run, and how far it actually gets elevated by the end of the run, that's the total rise from here to here. So, as a 21 foot run, we know this is 21. What's the actual rise here going to be? You could be surprised it's not really going to be very much. And let's throw our x in here again, because that's the part we don't know. And that equals 1 over 12. So now we can just write 12x equals 21 times 1, which is 21. And we can divide these each by 3 and get that 4x equals 7. X equals 7 over 4. Which equals 1 3/4 foot. Wow. If I got that right, that's not even a 2-foot rise for a 21-foot run. It's very gentle sloping. And that makes sense. And these wheelchair ramps are not designed to give people a workout. It's supposed to be a nice, easy way to just avoid the stairs. So they have a pretty gentle rise to them. This is a good one because it uses percentages, and those are a very important application of ratios. They're all over the place. Getting used to percentages, developing a facility for working with percentages is a good idea. People are going to throw them at you all the time. I don't think you can turn on the news one day out of the week without hearing about percentages in some new study. How accurate the percentages in the study are is questionable, but they're out there. And it's good to understand how to interpret these things. So, let's say we have, a whole bunch of participants, 4,887. Estimate the number who picked the number 3. Now that was 11.4%. And what does that mean? Well, that means 11.4 over 100, right? That's what percent means. That's the ratio of people who picked the number 3. Well, how many people does that represent? We say ratio, it's also the fraction of people who is the ratio of the whole, or the fraction. We multiply that by 4,887. That should give us the actual number. This gives us the fraction of people, which is 11.4 over 100, the ratio of people who chose 3 to people who were questioned. So if you actually perform the calculation, you should get 557.12. Well, 0.12 of a person isn't going to work out. So you could round this to 557. That would be the correct way to round a number. On the other hand, when you're talking about things like people, you don't really know how this stuff was rounded off. So 558, in other words, just bumping it up, because you can't have a fraction of a person. So any fraction is just rounded up so that you include the whole person. So I don't think 558 would actually be an incorrect answer, even though that's not the correct way to round. When you're talking about people, that's a little bit different, because fractions of people just don't make any sense. Well, what about the next part? You ask a participant what number she picked. Is the participant more likely to answer 6 or 7? Well, questions, frequently called surveys. And questions like this always assume that the person's going to tell the truth. I like to phrase the question such as, if you were to pick a person in this study at random, is it more likely that person picked 6 or 7? Leave out the part where you ask. I don't like those kind of questions, because it assumes an honesty in the human race that probably doesn't exist. And I don't see any reason to introduce that into a mathematics class. Your opinion of people's honesty is all yours. I don't think we should assume or not assume anything in a math class. So I don't like those kind of questions. I think we should have stated it. If you pick a person at random, is that person more likely to have chosen 6 or 7? That way, honesty doesn't even enter into it. And anyway, the answer is obviously 7. In fact, they're almost 3 times as likely to have picked 7 as 6. You just get that from the numbers. For instance, if you don't want to just go by the percentages, and percentages are only useful because they tend to put things on a scale of 0 to 100. They just put everything back to the same scale. So it makes it easy to compare apples to oranges in a sense, because you put everything back on the same scale. It's the same as questions you've asked. Where would you rate this on a scale of 1 to 10? Where would you rate this on a scale of 0 to 5? Well, percentages has put it on a 0 to 100 scale. But of course that's not absolute. It is possible to have 200% of something. That just means you doubled it. And it's not the most legitimate use of percentages. That's not really what they were intended for. For instance, in this case, why did we even need percentages here? We could have just actually listed the number of people. And if you knew the sample size, that would give you a fraction, I guess. Well, definitely would give you the fraction once you computed it. The question is, how important would that be? For instance, this is 10%, so we could just tell right off the bat, what's 10% of this? Well, just move the decimal point over one place, and we get 4887.7. We could have just written that in there instead of 10%. Now they could have written in actual numbers, like I wrote in numbers here. You can always do that, and you still get the same sense of how many people or how likely somebody was to pick a particular number in a relative sense. For instance, it's easy to see that if you pick a person at random, they're about 3 times more likely to have picked a 7 than a 6. You don't need percentages to see that. You can just see that from the actual numbers. But percentages are, as I say, they're extremely common. People use them all the time, whether it even adds any information or not. It's just such a natural thing to do. People always throw things into percentages. You have to remember that an awful lot of the things you see published, those aren't done by mathematicians. They're not even done by people who teach math. They're frequently done by people who majored in journalism or something like that. So they just do what they're used to seeing. Consequently, you're going to see percentages all over the place, whether they are really necessary or not. So it really behooves you to get used to percentages, develop a facility with percentages. By the way, when I did this down here, I didn't mention it. I hope you realized that 11.4 over 100 is 0.114. And when you're doing arithmetic with percentages, you can always do that. 10.7%, you just turn that into 0.107. That's the actual number that represents, because 10.7% means 10.7 over 100, which means 0.107, just like 11.4 over 100 here. Just move the decimal point over 2 places because you're dividing by 100. What about this last part here? Conduct this experiment with your classmates. Well, I don't have too many people in the room with me, so I'm going to have to skip that one. You guys can do that. What about the explanation here? Why might they be different? Well, gee whiz. I mean, do you even have to ask that question? I mean, it's like people are going to just randomly pick different numbers. It seems kind of obvious to me. If you had 10 different types of ice cream and asked people what was their favorite, and you had this sample of 4,887 people, and then you took a whole different set of people, why in the world do you expect to get the same numbers? In one group, maybe 10% of them liked strawberry ice cream. In another group, 15% liked it. It's absolutely no reason to expect the numbers to just stay the same in every single group. I guess that's what they meant by that one. I guess the short answer down here would be the numbers are different because people are different. I don't know what more you could say. Well, that's about it for now.